Now let's start B part 6, exterior algebra for physics and classical mechanics, and also applied to electromagnetism. So let's start on lecture 1, dual basis definition. Consider the tangent vector space, TPM. This is TPM over here, is a vector space V. Partial xi are the bases, okay? In this case is covariant basis, and AI are the components, contravariant components AI. Both belong to the space TPM. Now, this is by definition, the contravariant basis dxj belongs to the cotangent space, to cotangent dual space Tp asterisk m. Now the definition is the inner product of dxi d divided by dxi dxj is the chronic delta ij. Now recall that the tensor is a map such that you have the inner product, okay? This maps in a scalar. You see, this is aibj, is outside this inner, this scale, the inner product, and this is delta ij, is partial xi dxj. So you apply the chronic delta, this aibi. Now, for instance, for I is equal to 3, there's a dummy index, A1, B1 plus A2, B2 plus A3, B3, which is a real number, okay, by definition of a tensor. Now, real number would satisfy the definition of a tensor. Observe that the first order tensor A and B are invariant. What means invariant? They do not depend on the coordinate system. Okay, it doesn't matter if I'm working in the basis, covariant basis, or the dual basis. Doesn't matter. So this is A and B are invariant. So the inner product aibj, you see, just dxi dxj is aibj, delta ij is aibi. Now compare aibi with aibi over here. Now each element of the components, they are different, you see, completely different, but they represent the same real number, okay, as you see. So that's what means invariant. You see here, ai partial xi, ak dxk is the same vector, okay? This is invariant. Likewise, bm partial xm is equal bk and dk, dxk. You see, invariant is the same point P. If you move to another point, you see, so the invariant, they will be invariant at that new point. That's the point P. So it is important to remark that AMBM is equal ANBN, same real number at the point P, although each AM is different from each AM, and BM different from BM. See? So a scalar function, it is not this case, okay? In general, a scalar function, it is denoted as a tensor of zero order. You see? A vector is a first order tensor, and a tensor is in this case is a product, okay? Tensor product. AB is a second order tensor, and so on. That's important. Now, let's transfer this consideration here just to here. Likewise, a scalar is denoted as zero form. The one form is associated to AI dxi. You see, this is dxi, don't forget that, belongs to the cotangent space. AI are the covariant component at that cotangent space, okay? dxi, in this case, is a contravariant. AI is covariant, but both belong to the cotangent space. In this case, the second form number 2, is Aij dxi. This is a tensor product dxj, and so on. For instance, if you have Aijk dxi tensor product dxj tensor product dxk. You see, this over here is the form 3. Okay, just write this. You can extend this for any dimension. So that's clear. That's now called the introduction, okay, to the tools of stereo algebra. That's important. We'll continue now. Then I'll show properties, okay, of this basis, okay. This belongs to the dual space. See, dxi belongs to the dual space or the cotangent space. That's it.